A warm greetings to all the eminent delegates present in the International Summits and Conference on Material Science, Nanotechnology and Biomanufacturing Materials. I am RCSI, PhD scholar under the guidance of Professor Kaushik Pal from Bharat University, Chennai. The title of my presentation is Nanomaterials Enable Liquid Crystalline Optical Materials Towards Switchable Device Implementations and Exclusive Applications. These are the table of content of my presentation. In this presentation, I'll be explaining the fabrication method of CDS, zinc oxide, graphene nanostructures, liquid crystals, and the homogeneous distribution of these nanomaterials into hydrogen bonded liquid crystal and its remarkable properties. The electro-optic switching properties of this nanohybrid composite will also be examined. Green chemistry approach for the preparation of gold nanoparticles and its application is also explained in this presentation. Now let's try to understand what is this nanoscience and nanotechnology. We all know that in today's world, nanotechnology plays a vital role. From home to industry, this small but big technology has been used. So, nanotechnology can be defined as the manipulation of matter on an atomic or molecular scale. It deals with matter at a level that most of us find hard to imagine, as it involves objects with dimensions of 100 billionth of a meter, that is 1/800th of the thickness of a human hair or less. At this new dimension, they exhibit new functionalities and properties which find a lot of applications. Placing atoms as though they were bricks, nanotechnology will give us complete control over the structure of matter, allowing us to build any substance or structure permitted by the laws of nature. Thus, we can say that the goal of this technology is to make tiny devices called nanomachines. Applications of nanotechnology. Nanotechnology has been used in diverse fields like optical engineering, defense and security, bioengineering, cosmetics, nanofabrics, energy, medicines and drugs, nanobiotechnology, nano devices, etc. These are some of the commercial applications of nanotechnology. Fuel cell is a nano-engineered battery, light in weight and flexible just like a paper. Another energy application is the solar cell. Nanotube finds a lot of application in medical science. It has been used in targeted drug delivery system. Artificial retina and tissue regeneration are other applications that use nanotubes. And aerogel is a ultra-light material with low density. It provides effective insulation. Liquid crystalline material. Liquid crystals are a state of matter which has properties between those of conventional liquid and those of solid crystal. For instance, a liquid crystal may flow like a liquid, but its molecules may be oriented in a crystal-like way. There are many different types of liquid crystal phases which can be distinguished by their different optical properties. Liquid crystals are broadly classified as lyotropic liquid crystal and thermotropic liquid crystal. In thermotropic liquid crystal, the liquid crystal materials undergo a phase change from the crystal phase to the isotropic phase with an increase in temperature. Whereas in lyotropic liquid crystal, the phase transition occurs by adding or removing solvent. Based on the shape of the molecules, thermotropic liquid crystals are further classified as rhodolite, bent core, and disc-like liquid crystal. Nematic phase and smectic phase are the two phases of liquid crystal. In nematic phase, only the long axis of the molecules are parallel and the ends are staggered at random intervals. Whereas in smectic phase, the long axis of the molecules are parallel and the molecules are also arranged in plane. Smectic phase is further classified as smectic A and smectic C phase. Now let's have a look into the optoelectronic switchable device implementation by CDS nanowire liquid crystal composite. This figure shows the fabrication of CDS nanowire. CDS nanowire is fabricated using hydrothermal synthesis where aqueous solution of ethylene diamine, cadmium acetate and thioacetamide was prepared and it was left for 1 hour with continuous uniform stirring by a magnetic stirrer. Then 100 ml of ammonium solution was added which turned the solution into dark yellow. This produced mixture was again left for 3 hours at constant temperature and magnetic stirring. Then it was transferred into a Teflon line autoclave and maintained at 165 degrees centigrade for 18 hours. Then it was left at naturally cooling in open atmosphere. The yellow precipitate was collected by centrifugal separation, washed with deionized water and ethanol, and it was then dried under vacuum for 5 hours at 65 degrees centigrade. The obtained sample was dried out under continuous flow of nitrogen gas. Bent core liquid crystal was then fabricated, and then the synthesized CDS nanowire was dispersed into the liquid crystal to form a nanohybrid composite. This shows the fabrication of ITO liquid crystal cell. Here, these are the substrates which has an ITO coating, and the cell gap was maintained with 2 micrometer spacer placed between the substrate. Here, it was heated, and the CDS nanowire dispersed bent core liquid crystal sample was distributed inside the heated cell by the flow of capillary action. Microscopic and spectroscopic analysis. FESM helped to FESM, that is the field emission scanning electron microscopy, help us to determine the morphology and particle size of CDS nanowire. These images shows that the CDS nanowires are of uniform thickness and high aspect ratio and are well crystallized. CDS nanowires have very low diameter in the order of 7 to 10 nanometer and length in the micrometer range of 1 micrometer to 80 micrometer. The HRTM images also reveal the formation of uniformly shaped CDS nanowire. Selected area diffraction, that is the psi pattern, as shown here, indicate the polycrystalline nature of this nanomaterial dispersed liquid crystal. And this figure shows the uniform distribution of high yield CDS nanowire. Atomic force microscopy was performed, and these images indicate that the films are extremely rough, dense, and non-uniform. The surface roughness varies to 125 nanometer, and thickness was around 7.8 nanometer. Then conducting mode atomic force microscopy help us to understand the maximum flow of surface current, and it was determined to be in the range of 3 nanoampere to 12 nanoampere. Then energy dispersion X-ray spectroscopy, that is the EDS pattern. EDS spectra is shown here. The peaks of CD and S in the EDS pattern indicate that the K shell element cadmium and the L shell element sulfide exist with an atomic ratio of 50.5 to 35.5. It also indicates that the CDS nanostructure dispersed liquid crystal is associated with other chemical elements like sodium, chlorine, fluorine. Now, this shows the polarization optical microscopic images. These images are the images obtained for various phases at different temperature, and this is a clear indication that it can be it is functioning as an electro-optic switch. And this research work was published in Organic Electronics in 2019. Now let's have a look into the zinc oxide nanocomb dispersed into hydrogen bonded liquid crystal phase transition and novel switching. This figure shows the various steps involved in the fabrication of zinc oxide nanocomb. Here, zinc acetate dihydrate is continuously stirred into alkaline media, that is 5 mol of sodium hydroxide and 3 mol of potassium hydroxide. It is continuously stirred for half an hour. A milk type solution was obtained. Then it was transferred to autoclave at 120 degrees centigrade for 2 hours. It was then air cooled to room temperature, which results in the dark gray precipitate. Then it was washed twice with ethanol and followed by washing with deionized distilled water. The sample was dried with continuous supply of nitrogen gas, and the so obtained zinc oxide nanospike was then transferred through vapor deposition process into nanocomb with the development of thin ribbon-like stem and teeth-shaped structures on the stem surface. And to form the liquid crystal, 2 moles of non-eloxy benzoic acid is added with 1 mole of subric acid in dimethyl formyl. It was continuously stirred for 12 hours at room temperature of 30 degrees centigrade to obtain white precipitation in a dense solution, after which the excess DMF is removed and crystallized with dimethyl sulfoxide. Then for the synthesis of nanomaterial dispersed liquid crystal, typical amount, that is around 0.35 gram of zinc oxide nanocombs are mixed with 0.005% of pure liquid crystal suspension. It is then continuously stirred for an hour, which is then followed by ultrasonic vibration that enable the nanomaterial to be completely dispersed in the liquid crystal material. The obtained nanocomposite is then vacuum dried at 50 degrees centigrade for about 2 hours. Here, the ITO liquid crystal cell is again fabricated. The iridium titanium oxide, that is ITO electrodes, are of dimension of 4 millimeters squared. And here there is a spacer which forms a gap in between them. And the liquid crystal obtained is kept on a, the liquid crystal cell is now kept on a hot plate treated at a temperature of 5 degrees centigrade per minute. The synthesized hydrogen bonded liquid crystal dispersed with zinc oxide nanocomb are spread into this heated cell by capillary action. Microscopic and spectroscopic analysis. The shape and size of the zinc oxide nanomaterial was examined through field emission scanning electron microscopy at various magnification, as you can see in these images. The low resolution images, as you can see here in figure A, indicate that the zinc oxide nanomaterial on a flower shape morphology, and they are densely grown over the entire substrate surface. The close examination of this figure also reveals that the nanoflower morphology is formed by the aggregation of multiple one-dimensional zinc oxide nanospike. You can see that the nanospikes emerge radially from a central source in such a way that they create a flower-like morphology. And it is also found that the nanoflowers do not possess uniform diameter. And this figure, that is the figure B, shows the formation of self-organized single crystalline zinc oxide nanocomb. And this shows that the nanocombs are evenly spread and grown abundantly over the broad surface of the substrate. And this shows that the nanocomb consists of nano rod-like branches along the long ribbon-like stem. Then the high resolution TEM, that is the HR TEM, together with the selected area diffraction, that is a side pattern, is performed to examine the crystalline structure, size and shape of the synthesized zinc oxide nanocomb. These images were critically analyzed to describe the atomic structure. And they also demonstrate that the nanocomb teeth are associated along one side of the ribbon-like stem. HRTM images and the side pattern provides an important study of the crystal structure of the zinc oxide nanocomb. Then the percentage of the elemental distribution of zinc oxide nanomaterial dispersed liquid crystal is demonstrated by the chemical mapping as indicated here. This shows that the zinc occurs at a percentage of 56%, oxygen 28.5%, and the fluorine is 9.8% and chlorine 5.7%. Chemical mapping offers an effective approach of exploring atomic level structure, chemical and functional information of nanomaterial. The elemental distribution of zinc oxide nanocomb on silicon substrate is analyzed through the EDS pattern, as you can see here. The development of zinc oxide nanomaterial is indicated by the high peak of zinc and oxygen. It also confirms that the zinc and oxide occurs with an atomic ratio of 24.63 to 18.34. Then additional elements like aluminum, fluorine, chlorine are also seen here. The AFM results, as shown in this figure, indicate that the films are exceptionally rough, dense, and they are not homogeneous in nature. The surface roughness governs the way that the nanomaterial interact with external parameters such as light, doped materials, etc., and thus ultimately determining the functionality and properties of the material. Here, the roughness was determined to be around 4.9 nanometer. Then conducting more atomic force microscopy helped to understand the surface current. And here the current measured was around it was in the range of 7.9 nanoampere to 16.1 nanoampere. And this shows the polarization optical microscopy images. And here these are the images of various phases at different temperature. And again here this is a clear indication that this is functioning as an electro-optic switch. Now let's have a look into the graphene and graphene oxide. Graphene is considered as the strongest material, and it has a good electrical conductivity, optical, thermal, and mechanical properties. The oxidized form of graphene is known as graphene oxide, and it has plentiful oxygenic groups, and it demonstrates outstanding hydrophilic nature, dispersibility, and steadiness. And this shows the various steps involved in the fabrication of graphene. Here, graphene can be fabricated by thermal CVD on polycrystalline nickel film. As shown here, around 500 nanometer thick nickel film was evaporated on a substrate, that is a silicon substrate, and it was annealed at a temperature of 1,000 degrees centigrade for approximately 20 minutes with argon and hydrogen. Nickel grains of 5 to 20 micrometer in dimensions were formed. And by after chemical vapor deposition for about 10 minutes at 1,000 degrees centigrade, using methane and hydrogen, graphene was formed on nickel, and the size of each graphene is limited by the grain size of nickel. And here we are using copper catalyst instead of silicon, instead of nickel film. And this shows the fabrication steps of graphene oxide. And this method is known as the improved Hummer's method. Here, the mixture of sulfuric acid and phosphoric acid is stirred continuously for several minutes, followed by the addition of graphite powder. The mixture was continuously stirred by slowly adding potassium permanganate until the solution turns dark green. Excess potassium permanganate was eliminated by stirring the solution with hydrogen peroxide. The mixture is diluted by adding water, and stirring continued. Later, the solution was left without stirring for the particles to be collected at the bottom, and the excess water is filtered out. The obtained mixture is cleaned thoroughly by centrifugation with hydrogen chloride and deionized water. The gel-like product obtained is then vacuum dried to obtain graphene oxide powder. Microscopic and spectroscopic analysis. The AFM measurement suggests that the surface of the synthesized graphene film is non-homogeneous, and it exhibits small peaks. And this figure displays the SEM and the optical images and the corresponding Raman spectra, and the maps of the 2D, D, G, and 2D bands. And this all displays the defect density and film thickness. The color contrast under the optical microscope and Raman spectra were used to determine the thickness and uniformity of the graphene film. The Raman spectrum from the lightest pink background reveals the typical monolayer graphene, and the blue indicate the bilayer graphene, and whereas the tri-layer graphene is represented by the dark green. The SEM pictures in this figure demonstrate that the thickness variation is more clear, and existence of more than one layer in the flake is clearly visible on this maps. And all these indicate that the single layer, monolayer graphene was fabricated more than the other layers. And here, these are the SEM images of the graphene oxide. This is the SEM image of the graphene, and this is of the graphene oxide. And these are the EDS pattern. Here, this is of the graphite, and here there is no presence of oxygen, but here you can see the presence of oxygen, which shows that the graphene oxide has been fabricated. And this is the Fourier transform infrared analysis of the graphene oxide. Here the bond of the CO and C double bond O shows the presence of formation of graphene oxide. And this research work was published in the Journal of Molecular Structure. We all know that the nanomaterials are synthesized using chemicals that are hazardous to the environment as well as the human beings. Green synthesis has numerous advantages over chemical and physical method, which is most beneficial as they do not require any toxic stabilizers and chemical. The green synthesized technique chooses water as solvent and uses renewable and ecological materials such as plant extract, food waste, etc. instead of the highly toxic reducing agent and stabilizing agent. Here, I am going to explain the green chemistry synthesis of gold nanoparticles using tamarind indica fruit extract and its biogenic application. Gold nanoparticle can also be fabricated using other fruit extracts like citric fruit extract, mushroom extract, food waste, etc. For the preparation of tamarind indica fruit extract, a small piece of tamarind indica fruit was kept in 50 milliliter of hot deionized water for 5 minutes. Then this tamarind was squeezed well. The extract of this fruit was then filtered and stored. The tamarind indica fruit essence drop was mixed into the tetrachlororic acid. Then the color changed from light yellow to purple brown, indicating the formation of gold nanoparticles. Microscopic analysis of the synthesized gold nanoparticle. Here the gold nanoparticle with dimensions of around 50 nanometer and having an in vitro stability was confirmed by the FESM images. The morphology and crystalline nature of the gold nanoparticle was confirmed by the HRTM images. And this is the UV visible analysis, and which confirmed the presence of gold nanoparticle at a wavelength of 515 nanometer. Because of its bacteriostatic, antioxidative, and anti-corrosive pattern properties, gold has been utilized for medical applications. Here, the photothermal therapy application is being explained. Here, the gold nanoparticle has been loaded with drugs, and it is then using the magnetic field, it is guided towards the tumor cell. The tumor cells will swallow these gold nanoparticles, and the light energy light energy provide, which are the light energy will be converted to heat energy by this gold nanoparticle, and it will activate the death of the tumor cells. And this research work was published in the Materials Today Chemistry. And these are some of the other exclusive publications. And these are some of my achievements. Conclusion and outlook. Various nanomaterials such as CDS nanowire, zinc oxide, nanocomp, graphene oxide were successfully synthesized and investigated through various spectroscopies. The result demonstrate that the nanomaterials dispersed into liquid crystal regulate the electro-optic properties of the liquid crystal system and thus contribute to the innovative switching mechanism in liquid crystal and other optoelectronic devices. Gold nanoparticles hold great potential in bioimaging and thermal treatment with their ability to be directed towards targeted cells. Similarly, nano-assembly vaccines have the potential to reshape the future of adjuvants and provide new generation vaccines. Acknowledgement. I respect and thank the organizing committee for providing me an opportunity to do this presentation. I owe my deep gratitude to my research guide, Professor Kaushik Pal, who took keen interest and guided me all along by providing all the necessary information for developing a good presentation. I'm thankful to and fortunate enough to have the presence of esteemed delegates and experts in the field of nanotechnology. And these are my references. Thank you all for your kind attention.